for this part. You guys literally live in one of the greatest times to learn things. I mean, right now the pandemic, Roni sucks, but other than that, I mean, think about it. I say this all the time. You have the world at your fingertips. Most of you have a smartphone. Every piece of knowledge the world has, you can access at any time. And most of you don't even pay for it because you're either using your parents' cell phone plan or the Wi-Fi somewhere, right? And yet, what many people do is, in my opinion, you use it wrong. It's okay to have fun and play games and search and do all that, but I'm saying school-wise, instead of just getting the answers, when you find homework solutions or you find other things on the resources, you need to learn from them, not just copy them down, learn from them, become a better learner. So I can't emphasize enough how important I think that is. Bo, your name pops up here. You great. I yelled at you in the summer a few times, right, in calculus, because I'm just going to give you the answers, okay? And I said, Bo, give me the work. And then you decided, still against my wishes, of giving me the work at the end. But I still forgive you, Bo, because you at least listened to me. The point is you want to show that you understand how the reasoning goes. Again, let's not get it twisted. Most of you are not going to be answering probability questions 5 years from now, 10 years from now, right? That doesn't mean that it's not worth your while to learn it now, because it's teaching you thinking and reasoning skills. No one says that 10 years from now, you're going to be sitting at a desk and your boss is going to say, we need to know what's the probability that this happens, right? It's probably not going to happen for any of you. I don't know, maybe some of you go work in the financial market and you do stuff like this. And maybe you're a math teacher, I don't know. But most of you probably won't do math ever again after this class for some of you, right? But that doesn't mean it's not worth your time to learn it now. Trust me, you get stuff from that. And not just math, any class, right? Hell, if I never would have taken English 200 in college, I never would have known what the word pensive meant. You believe this? All these nerds, I remember sitting in this school and good old Meadville, PA, and I said, what does pensive mean? And all the nerds looked at me like, how stupid are you, O'Grady? It means thoughtful. Do you know what pensive means? That's an SAT word. That's what I call a wealth test word, right? SATs, standardized test, or in O'Grady's world, wealth test. The more money you have, the more likely you are to score higher. Causation, correlation, I don't know. All right, let's do math. But before we do that, though, does anybody have a question about exam, anything? We good? Itch. Got my NASA shirt on. Forgot I had this shirt. I said I'll wear it today. Why not? All right, here we go. Fun times. So today's a hugely important day for us. What we're going to do today is we're going to talk about perhaps one of the most useful probability distributions, but also probably one of the misused probability distributions that the world has ever seen. It's interesting because it literally is something that has an effect on your life, and most humans don't really even understand that, nor do you care, I guess, and nor maybe should you care. But I find it fascinating in and of itself that this sort of thing we're going to talk about, this, as I alluded to at the end of last class, the normal distribution, this bell curve, as it were, as it is, I should say, how much this affects your life, for good and bad, actually, if I'm being honest. To sort of set the stage, let's think about what we've been doing. We've been studying probability distributions, and we haven't made really, I asked it on the homework, but I haven't made a big deal about it to this point because it's just one more thing to confuse you. So I say, why bring it up? But the distributions we've been studying are what are called discrete probability distributions. And if you look at one of your homeworks, I think I asked you to describe the difference between discrete and continuous distributions. You might remember that on one of the recent homeworks. And I didn't bring it up in class. And the reason I didn't bring it up in class right away is because I didn't want to have one more thing that, when you guys hear definitions and terms, it's like one more thing that you need to memorize, which I don't want you to think of things that way. What I'd like you to do is understand the differences in certain things. So let's do that. So today is our big day. The normal distribution. So let's look at a sort of a basic example, the one we use the numerous times. Let's say we're going to flip a coin 10 times and we want to count the number of heads. Right? So suppose the random variable is the number of heads we flip. How many options are there? There's 10 options. You can get 0. Well, I guess technically you can get, right, or through 10, correct? So if I flip a coin 10 times, how many heads can I get? I can get 1 head. I can get, well, don't forget that I can have 0 heads, right? The point is I can't get like 3.6 heads. That doesn't make any sense. And so when we're doing something like a coin toss or rolling dice, we say that these are discrete because they cannot assume, they can't take values other than specific ones in the sense where I can't get 7.2 heads. I can either get 7 or 8. Does that make sense? In fact, I could develop some sort of experiment where maybe I can get 7.1 of something, 7.2. Maybe I'm doing your grades. Maybe on a grade you can get anywhere between a 0 and 100. But maybe I say you can have a 91 or a 91.1 or a 91.2. That is still considered discrete because there's still sort of gaps in. And this is, I hate to even bring this stuff up because it's more confusing than anything. But whereas there are other experiments, for example, suppose I'm going to measure the height of everybody, as we talked about on the very first day of class, then theoretically your height can be essentially any number between maybe 0 and say 10, right? Theoretically. We might round and say you're 5'1", but really if we wanted to be more precise, you might be 5 foot and 11/12. Does that make sense? So in many ways we think of that as what we call a continuous random variable. Because theoretically you can assume any value between two numbers. So again, let me illustrate this again. If I'm flipping coins and I'm counting heads, then that is what we call a discrete random variable. If I'm taking humans and measuring height, or maybe we take your body temperature every time you come into this building, right? That is a continuous random variable. So what I'd like to show you is something we've done before. So I'm going to pull it up. Let me find it. Where did I put it? Give me a second. I lost it. I just had it. Ah, there it is. No, that's not the one I wanted. There it is. So I'm going to share something with you real quick. And what I'm going to do is I'm going to roll some dice. I'm going to roll 2 dice. And I'm going to get the sum of it, right? We already talked about how the most likely sum is 7. There's the most options for 7. The least likely are 2 and 12, right? Because the only way to get a 2 is a 1 and a 1. The only way to get a 12 is a 6 and a 6. So those are the least likely, but 7 you can get 3, 4, 5, 2, etc., right? And so what I'd like to do is I'd like to run that experiment 1,000 times. So for, of course, I'm in the wrong place. Idiot. Okay, now we run it here. What do you mean? It's right here, homie. So what I did is I played this game 1,000 times, and I would like to look at the distribution of the results. What happens? And so I'm going to make a graph of it. Of course, it's going to take a while because the first time you load it up. So I'm going to do it two ways. I'm going to look at the numbers, and then I'm going to visualize the numbers. So 4 and 7 years later, it'll pop up. I hope. Maybe I should screen the screen for this, because that way at home they can see. Here it is. So look at this. Let's look at this triangle, what it's saying. This is saying that of all the values I rolled, I got 7 the most. I got 2 and 12 the least. And look at the symmetry here. It's very symmetric, right? As we would imagine, dice are, it's symmetric, right? Now let's look at the numbers. So 285 out of my 10,000, I got a 2. 285 times out of my 10,000, that's pretty rare. It was exact. And look at this symmetry here. These numbers aren't exactly symmetric, but it's pretty close. And so this is our distribution. This is what we're saying. So let the random variable be I roll a k, where k is 2 through 12. Well, here's 285 times I got that. 561 times I got that. Now, think about it. What would we expect? Well, if you do the probability, what's the chances that I would get a 2? Well, how many options are there? How many options are there for a 2? There is one option. And how many total outcomes are there? 36, right? So the chances I roll a 2 is 1 in 36. If I hit enter, I get 0.027. What are the chances? So let's go back here for a second. I ran that 100,000 times. No wonder it's off. Where did it go? I just lost it. Ah! All right, I just lost something. Where did it go? This is never good. You don't prepare for this. All right, let's rerun it. I'm going to run it 1,000 times. So you notice when I only run it 1,000 times, I lost some of my symmetry. I didn't do it enough. I have some events that we might, maybe I got more 5s. And in this case, it looks like I got 5s more than I would have thought I would have, right? So we can run it again, and let's see. We did it 1,000 times. What is our picture? Now our picture looks a little more like it did originally, a little more symmetric. Now, if I increase the number of times I've run it, if I go back up instead of 10,000, I go back up to 100,000. Actually, no, that's 10,000. What am I saying? I can't read. And you see I start to get my symmetry back. So, but what I want you to concentrate on are these percentages. 2.4% of the time, I got a 2. Does that make sense? Run it again. Now I get 273 2s, 271 12s. Is this what I should be expecting? Should we not expect that, since the probability, as I said before, of a 2 is 1 over 36, should we not expect, and if I take what is this number written in terms of a percentage? If I multiply this thing by 100, to put it in percentage, what is it? 2.77. Look at this, it's pretty close, right? So the point we're trying to make is if I run my simulation, if I roll dice 10,000 times and I look, if I count the number that I get of each roll and I plot it, I get this very nice symmetric thing. And so this symmetry is something we want to take advantage of. And it turns out that in the real world, there's many continuous things that have this type of symmetry as well. Does anybody have a question about this? All right. Going once. Going twice. All right. Now we're ready to write some scary stuff down. So this is going to be scary. So don't lose your mind too much. So the normal distribution is what we call a continuous distribution. So when we did the coin toss experiments, those were not, just like cards and dice, they were not continuous. This is a continuous distribution. So you need to remember some things from math class. It uses the famous number E, which we saw last week. And if you don't know what E is, you can always Google it. So I always hate this part because it gets scary. It also uses another famous number. So I guess. So by the way, these ellipses tell us that these numbers, they go on forever and ever. They're irrational numbers. So let's talk about the simplest case. And this is what's called the standard normal distribution. With mean mu equals 0 and standard deviation sigma equals 1. Now, if you go back to last week, when we gave you 3 specific distributions, you'll notice each one of them had a formula. It was a function. So the standard normal distribution has probability given by the following. F of x equals 1 over the square root of 2 pi times e to the negative 1/2. I guess we'll be consistent with the book. We'll use z.
So what is z again?
So, okay, there's a good question. What is z? Z is a variable. So in the ones where we're discrete, our variable was something like k, right? Or x equals k, where k was like 0, 1, 2, 3, 4, 5. Now we're talking a little differently. Now we are thinking about z is a random variable. But the idea is that z can assume any real number, not just 0 through 10 or not just 2 through 12. It can assume any real number. Now, there's a lot happening here, and the sentence I wrote is somewhat misleading. Perhaps I should say it a little. Perhaps I should say it a little cleaner, so that it's not so confusing. Before I do that, does anybody have a question? This is a function or an equation that you should have seen in an algebra class at some point in your life. If we go to the internet, I can go to Desmos and I can show you what its graph looks like. And this is why we call it the bell curve. So if I graph y equals 1 divided by square root 2 pi, and then it's e raised to the power negative 1/2. I'll use x here squared, and then I zoom in, change my scale. It looks like this. So it's this bell curve. So imagine, okay, before we do anything else, imagine why something like this would be sort of useful. So let's just sketch the graph here. And I want you to think of that example we talked about before where we talked about heights. If graph looks like this, if we talked about heights, we would imagine that if I said, let's go measure 10,000 people, it is more likely that I go and measure these adults that when I put down the heights, if I did them like I did with my coin toss earlier, the heights would be resembled by this curve. Now, we wouldn't imagine that it's at 0. We would imagine the average height is somewhere like 5'6" or something like that. And what we imagine is there'd be very few people that were like 3, 4 feet, adults, right? And there'd be very, very few adults that were like 8, 9 feet tall. most of us would be bunched and there'd be some symmetry here. We would imagine. Just like when I flip the coin, by the way, I have some symmetry. I'm very unlikely to get lots of 2s, but I am much more likely to get lots of 7s when I roll 2 dice. Do we understand that? So if I use the skills I learned in my math class and graph this function, its graph looks like this. Now, what we have to understand is how when I wrote here, which is sort of a little misleading, I said the standard normal distribution has probability given by. That's sort of misleading because the probability is based on this particular function, but it's based on something that's a little not clear from the way I've written it down. Does anybody have a question before we get in that a little more? Okay, now let's think about back to our dice example. How is the probability related to this? So let's go back to this figure. One way to think about it, probability, is that this rectangle is smaller than the 7, right? So really one way to think about this is area. If I asked you, what's the probability from this graph, what's the probability you roll a 2, 3, or 4? One way you might think about it is add up these areas and then divide it by the total area. Do you understand what I mean? Why would I say that? Because, for example, when I showed you, when I actually showed you, let me show you the screen. Go here. When I show you this, that's what we're doing. This is, if you think about the height is the number, well, the height and then the width is just being 1. I mean, you could choose it to be anything, right? But the area of that rectangle would be 273. So the probability of getting a 2 would be 273. It's divided by 10,000 or 100,000, however many I did. Does that make sense? So one way to interpret these probabilities of these discrete variables is on a bar chart. You could think of it as area. I'm not saying you're thinking of it that way. I'm telling you can. And so we want to naturally, again, how could we take these ideas of coins and dice and extend them to real things like loans and interest rates, and does medicine work? Does it not work? How do we extend these ideas? So what we need to do is we're thinking about, I am thinking about these probabilities, which, look, this simulated probabilities are matching my theoretical ones. I just showed you that. Look, the probability of rolling a 2 is 2.7%, right? Well, it turns out that matched. I was accurate to 1 decimal point when I did the simulation, 100,000 times or 10,000 times, I forget.
I saw a video this weekend that kind of relates, but doesn't really relate. It was about like going to a carnival and getting scammed on like the games and stuff. And
that relates, yeah.
And the probability of how you would like play it, but there's like different ways that they take to be able to trick you. So it kind of relates in the fact that like you throw in 2 of the rings on a ring toss game, what's the probability of you getting like the big prizes? And they said like really slim chances, and they only cost like I think 49 cents for the carnival to be able to pay for them, and you end up paying like $1.75 to play.
Well, that's the whole way a casino operates.
Right. So
it's exactly how it works. The probability is in their favor, which particularly means in the long run you're going to lose, and you're going to lose, and you're going to lose, and you're going to lose. That's how it's designed. Right? I mean, they're not there to make you rich, right? They're there to make someone else rich. I mean, I don't mean to say that in a negative way, right? But that's exactly right. I mean, I tried to illustrate. I tried to illustrate that with when we talked about the dice game. What's more likely, rolling a 2 when you roll, 1 dice, or rolling a 6 when you roll 6 dice, or rolling 2 6s if you roll 12 dice. We're trying to understand that the intuition, even though we think it's in our favor, it turns out that slight bit is not. And in the long run, you're out. That's the essence of how casinos operate. Okay, so if we want to think about that, then that tells us then, and this is quite interesting, in one of the reasons mathematicians like myself and others have a hard time trying to, we teach this class And the other people in the other disciplines want us to teach you about the normal distribution. The hard thing to say is, though, is to understand it fully requires math at a higher level than most of you have taken. And the reason is not just that this looks scary and most of you haven't had enough experience with that. That's bad enough. But it turns out when you want to define probabilities using this thing, you have to talk about area. And you have to talk about area under a specific region. Just like the probabilities of the binomial distribution could be thought of as area of rectangles, we are going to think about the area under this curve as a way of defining probabilities. And most of you don't even realize this, but you've never been taught, unless you've taken calculus, how to determine the area of a curved region. Think about this, mind F. If I said to you, I'll give you 10 grand right now to define area, can you do it? No, not one of, well, maybe you. I still think, Anthony, you'd mess it up. You would mess it up because it's been a while, right? Anybody else have calculus here? You'd probably mess it up, right? It's actually a very complicated idea. And so what the real world figured out is, since most humans don't want to learn calculus, we're going to sort of skirt the system. And so let's ask the question here, since I phrased it. How do we assign probabilities? Using this, what is called a function. So it turns out we use area. So if something can be modeled by a standard normal distribution, and like we said, things like height, now height's a little, I should have used a better example. Height is more of what we call normal distribution, because the mean can't be zero. Is the average height 0? No, but the mean might be like 5'5". So that's a more general case of what we're doing. But the idea is, how do we assign probabilities using this? So we use areas. So unfortunately, this requires calculus. And that's okay. We can skirt the system. You don't need to know calculus. And even if you learn calculus and forgot it, it's okay. So let's draw a picture. So here's my X and Y axis, which I'm trusting some of you remember. I don't know. And it has this, here's the curve of our normal distribution. By the way, you might remember these things are called asymptotes over here. Maybe you remember that word from a math class. The idea is that we have this bell-shaped curve, and then the blue, oh my God, I'm having a heck of a time drawing this today. The idea is that the blue curve keeps getting closer and closer to the x-axis. In both directions. So it's kind of hard for me to draw that, but really the way you want to think about this is this thing. As I said, it's an asymptote. It keeps coming down closer and closer and closer. And so let me talk about how we're going to do this. Let's take this red thing. And so here's how we define probabilities. What I'm going to do is I'm going to shade this region red. And I am going to label some arbitrary points. So don't let this scare you, but let's say we'll call this K. And so what we write is the following. We say the probability that our random variable Z is less than K. This is going to be defined as the area of the red region. Now, when you take calculus, you learn this thing called integration, and integration is the tool that allows us to answer the question of area. When you're children in school, you learn area for rectangles and triangles and then polygons, but you notice they tell you what the area of a circle is, but they don't tell you why. They just tell you to memorize it. Area of curved regions is actually a very, very difficult concept. In fact, it took human beings, a couple thousands of years to figure it out. We didn't really figure it out until the 1600s when someone invented calculus, Newton and Leibniz. Oh, okay, I wrote this wrong. Let me be clear. I'm hedging myself here. I'm gonna be more clear. This is really the probability that 0 is less than. Okay. So let me be very clear what we have here. K is a fixed number. Z is our random variable. So the old-fashioned way that you would answer this question, since we don't know calculus, is you would look up a table. Maybe some of you are familiar with this. So let me share something with you. But now we have technology to do it for us. So say I go to the internet, and if I Google standard normal table, and if you look in the back of your textbook, you'll see this. What you'll find is you'll find a table that looks something like this. And the way that you would calculate these areas is not to use calculus. You will steal what someone else did for you. For example, someone else made this table. And so for you to calculate probabilities, you don't have to do any math. You just have to figure out how to interpret this table. Does that make sense? And we'll teach you how to do that. But that's somewhat unnecessary nowadays because we have calculators that can do this for us. We have apps on our phone. We have websites that can do it for us. Do we understand that? Does anybody have a question or a comment? So let me go back to and make this point. I want to reiterate it. We're going to be able to define probabilities using the area under this curve. And these are useful. Look, think about what's happening here. We're making a definition. We're saying if things tend to be normally distributed, or if they're normally distributed, or if we think they are, then we can analyze them and we can define a probability through this. Just like you defined a probability for flipping coins. We had the distribution of the binomial distribution, I should say. This is just a distribution. Sometimes it's useful, sometimes it's not. The difficulty for us as we see it right now is the way it's defined is we have to calculate area of a curved region. And so since we don't, and by the way, that calculation is quite difficult to begin with. Does anybody have a comment or a question? So let's state this one more time. In general. So in general, the probability that the random variable is between any two values, I'll call A and B. This is equal to the area under the curve from A to B. And then we can also define, say, the probability that Z is greater than a number. Or the probability that Z is less than a number in a very intuitive way. So perhaps the best way to do it is to just draw the pictures. So let's just draw two pictures. Here's my curve, this bell curve. It looks like this. It's not the best picture. And here's my other one. So if I want to do less than Z, then what I do is I take the whole area, excuse me, up to K. So if this is K, I go all the way up to here. Shade this region in. If I want to do greater than K would be to the right. So this is the probability that Z is greater than K. This is the probability that Z is less than K. And K can be any number, doesn't matter. You can do this on Excel, as I said. You can do it. Software can do this for you. You can look it up. All right. All right, now here's what's even more scary. There's a general case of this. This, again, the case we're talking about, and this is the one we're going to work with, is when the mean is 0 and the standard deviation is 1. However, in the real world, we know that most things aren't that. Heights are not distributed with mean zeros. The average person, 0 foot. No. Many things aren't. So if we have a bunch of data, its mean and standard deviation could be lots of things. And so we need a situation to generalize that. Do we understand what I'm saying? And this is going to look even more frightening, and I do feel bad, but the good news is you only have to know the standard one to get all the answers. But you have to know how to go from the general case to the standard one. So don't shoot the messenger here. Oh boy. So let's write it down like this. Since most data we want to study does not have mean mu equals 0 and standard deviation 1, we need a more general formula. So one of the things that you guys learned about in an algebra class, and I'm not saying you need to remember it, but one of the things you would have learned is if you have a functions graph, you were taught how to shift it left and right and up and down and do all that. And you guys were like, oh my God, this is crazy. But nonetheless, you were taught that. That was something that was in an algebra curriculum. You probably learned it and forgotten it. But if we want to take our guy that has mean 0 and we want to shift it left or right to have a different mean, there's a way of doing that. And then if we want to change its shape, do we want to make it steeper? Do we want to make it flatter? There's a way of doing that. And so the general formula has this: f of x equals, don't get mad at this. Now it's 1 over the sigma times the square root of 2 pi times e, now this is the part that's also scary, minus x minus mu quantity squared all over 2 sigma squared. So what you'll note is if you replace sigma with 1 and mu with 0, you get what we had before. So note that if mu equals 0 and sigma equals 1, this becomes the standard normal distribution. So all this is it's the same curve, just shifted left or right, and it might be a little steeper, it might be a little taller, but it has the same idea. It's still bell-shaped. So if you go and you could sketch this, does anybody have a question about it? And by the way, at this level of course, you don't need to get freaked out about this thing. You don't have to have it memorized, right? The more you understand about that, the better, but you're going to be able to answer questions just by looking numbers up in the back of a book or typing something into an app or a calculator. Now, I'm not saying you should want to do that. I am telling you, I would love for you to try to understand this, but no one's going to ask you to recite this, right? It's a scary looking creature.
What tells you, like, what's the x variable or the x and y axis? Like, how do you read it?
How do you read it? This is right. So you might remember this from an algebra class. If you take your variable and subtract something from it, if it's positive, that shifts it to the right. So that minus mu shifts the whole thing to the right. So instead of it being centered at 0, it's now centered at mu. Do you guys remember that? You called it shifting in algebra class. Yeah. Yeah. And so then what this sigma does is, think about it. When sigma is large, you're taking 1 and you're dividing it by something. So it's shrinking it, right? And so that's flattening it. But as it's flattening it, it's making it wider. Think about that. So it's really fascinating. One of the things a lot of students have trouble with is what I like to call number sense. And that's probably, I mean, I don't know. I think it's gotten worse because your generation, you guys are more reliant on calculators, which is good and bad, right? It's good because who wants to do arithmetic by hand, right? I mean, there's no engineer sitting around, building rocket ships without using a computer, right? But at the same time, when you're a kid and you go immediately to calculators, you start losing out on number sense and how to understand what happens when I take the number 1. And if sigma is larger, it shrinks. But if sigma is smaller, it actually becomes bigger. For example, take 1 and divide it by 1/2. It actually becomes bigger. It becomes 2. Right? 1 divided by 1/2 is 2. But what is 1 divided by 3? It's 1/3. So these are the things we lose, these number sense. The moment we go and just use decimals, we start losing these ideas. So perhaps the best way to see this is to draw what it looks like. Now, let me draw, and I'll be very careful here. Let me draw an XY axis. So here's my X and Y. So we'll be very specific. We call this our x-axis and this our y-axis. And now what we're saying is now it's shifted. So here's my mu now. And what happens is this creature's is shifted. It's now symmetric about this line, not the y-axis anymore. So this thing has it's going to come up and go down like this. And once again, we call this a horizontal asymptote. You might remember that word from an algebra class or a calculus. And there's one over here too. So that blue line, it never touches the x-axis. It just keeps getting closer, closer, and closer. And of course, you might say, how is that possible? Well, here's a simple example of a horizontal asymptote. Take 1 and divide it by something. Divide it by 10. Divide it by 20, 30, 40, 50, 60. Can you ever get to 0 that way? No. In fact, there's no smallest positive number. Believe that. Think about that. If you start with 1 and cut it in half, take anything. I mean, this is a really good mind F if you understand what I'm saying. Take anything that as 1 unit. Take $1, cut it in half, you have 50 cents or half a dollar, right? Cut it again, you have $0.25. Cut it again, you have an eighth, a 16th, a 32nd, a 64th, a 128th. You never, ever, ever hit 0. And so what these asymptotes mean is the further out I go to the left, the closer and closer the output of my function, the blue line is close to the x-axis, and similar over here. Keeps getting closer and closer and closer. And that's useful for us because if we think about height, then we know that what is the probability that someone's going to be 27 feet tall? Well, we would expect that it's damn near 0, right? Does that make sense?
Maybe that one.
Yeah. I mean, yeah. And what's even more cool about this is it has certain symmetries. Then when you talk about the standard deviation, that there's all kinds of symmetries. For example, if I go, I'm gonna put this in red. Here's a cool fact. And if you look this in the book, they give more of these, but let's just say for the sake of it here and here, this is the mu minus the standard deviation, and this is mu plus the standard deviation. And what's pretty cool about this is the following, that roughly 68% of area falls, so this creature, within one standard deviation of the mean. Whew. Does anybody want to ask a question about this? Comments? I mean, it's a little overwhelming right now. I'll be deciding. I'm just kidding. Yeah, I mean, it is. It's a difficult concept. All right, so here's the key. going back to the math part of this, how do we shift it? And what does that mean? Well, being that we can shift, that's nice for us because we can take any normal distribution or any normal random variable and convert it to a standard normal one. So here's a key idea. We can always transform a normal random variable to a standard one. So here's how you do it. You reverse the process. So suppose X is a standard or excuse me, not a standard, a normal random variable. Darn it. Now, if you're normal, what do you have to have? You have to have a mean, mu, and standard deviation, sigma. Well, then z, which is x minus mu divided by sigma, is a normal, or excuse me, a standard normal. Distribution, or excuse me, standard normal. There's a lot of words, they're confusing, I know. Standard normal variable. So what this does is this makes it easy for someone. I mean, again, in modern times, it's not so important because we have machines and software that does this for us. But before computers and calculators and easily accessible technology, the only way we could compute these things were to look them up in a book. And so that's why we call it the standard one, because if you just have one book that has all these values, then you only have to look things up in that book or in that table, for example. Does anybody have a question or a comment? Going once, going twice. So one of the things I don't like to do is typically when this is introduced in a book, they do this and then they start doing examples, but I feel like that's an overwhelming thing. What I want you to concentrate on, and I hope you will before Wednesday, is the idea that, you know, imagine not trying to understand the formulas as much as think of the symmetry of the picture and think about examples that you could maybe pinpoint, not just, you know, not just heights. Think of another good example. If we take temperatures of people, say I go take the temperature of the body temperature of 10,000 people right now. Do I expect that there's going to be lots of people with a body temperature of 193 degrees? No, right? We'd expect most people to be around 98.6. So we would imagine that it's normally distributed. Would you not imagine that? We would think so, right? I'm not saying it is, but we would imagine that would be a good model for it. So to solve problems, it's so to solve problems involving a normal distribution, we might convert first or convert to a standard normal distribution. You don't have to, but you can. So let me explain what I'm saying. And this is completely out of context, but just while it's in our head, here's what I mean by that. Suppose X is normal with mean mu equals 4, and I'm just picking numbers out of the top of my head, and standard deviation equals, let's say, 0.25. Then, for example, the probability that X is greater than, I don't know, say greater than 5, well, we can replace this. What I can do is I can rewrite this in terms of Z. So if I look at the previous page, X and Z are related a certain way. So now it becomes an algebra problem. How are X and Z related? Well, X is equal to, if you look at this formula, you can solve it for X. I know this is algebra. Your boy's like, oh boy, I hate this. Multiply both sides by sigma, and then add mu to both sides. So if you look at this formula also tells you that X is equal to sigma times Z, correct? Plus mu, if you do the algebra. Take sigma to the other side, you multiply, and then you add mu to both sides. So I can replace that with sigma Z. So this is the same thing as sigma Z plus mu greater than 5. And then I can do the same reasoning. This is the same thing as the probability that, plug these numbers in, which sigma? Sigma is 0.25, so this would be 0.25Z plus 4 is greater than 5. And then if I take 4 to the other side, I get probability of Z is greater than 1 divided by 0.25. And I've converted it to a standard normal variable. So this is kind of one of the strategies that you can use. And right now we haven't given you any context. I haven't given you any problems, and we're going to do that on Wednesday. But right now we need to understand that we can do this. Does anybody have a question or a comment? So I'm going to post some assignment for you this afternoon. It's not going to be due until, we'll talk about the problems Wednesday. But I hope you'll start looking at it tonight, or at least tomorrow before Wednesday, because that's really where the learning happens. You trying to understand something and then finally seeing the light. So hopefully you'll do that. Does anybody have any questions or comments before we wrap it up? All right, well, thank you guys very much. I appreciate it. Hopefully you learned something. It's not too overwhelming. If it is, yell at me. All right, guys, take care. Thank you.